Welcome to Ask and Learn.
We'll be looking at virtual work for this particular problem. We want to determine the magnitude of m. Okay, we have m mass hanging there. All right, and we have this rod OAO. Okay, and this angle is theta. And of course, when this angle is theta, and when this rod OA becomes horizontal, to be equal to the okay DO. So let's call this DO, this O. All right. So therefore, if we trace this angle, all right, let's draw this one well. Okay, there'll be an angle there. So this angle is going to be oh, there's something there. Okay. So this angle here is this our mass m, right? So there's an angle here. This angle is 90 degree minus theta, right? That to can call this, say let's call here h, this distance, and let's call from here to the datum at OD. Let's call it uh, y subscript 2, all right? And let's call here b, and let the distance AB, let's just represent it with f, okay? And there'll be the height of this one. Of course, this one will weight of this one will act at the middle. Therefore, we can just get the h for this one. Let's call it y subscript 1. And of course, okay, so we've done this height is given as 3 from the datum to the top there. So we can just, for the rod OA, it is given to us to be 1 meter. Therefore, since A will coincide with D when the rod is horizontal, DO is also 1 meter. Okay, DO is 1 meter, right? So that to look for determine y substitute 1 is going to give us to be it's going to be half times 1 length sin theta. All right. So to solve this particular problem, we will actually um, determine the potential function, okay, and differentiate it with respect to theta, okay, and set it to 0, plug in the value of theta to determine uh, the mass, okay, all right. So have that to be that, all right. So if we do the same thing as 0.5 sin theta, okay. Now we will look at so for the potential energy, okay, for the total potential energy, we are going to have this to be equal to Of course, for this mass for the rod, the weight of the rod is going to give us the potential energy is going to be positive, okay, because it's above the datum. The center of gravity is above the datum. For the rod above the datum, we consider DO. Right now, we can look at the mass. For the mass, we are going to have since A coincide with D when OA is horizontal. Therefore, OD is equal to 1 meter, which we have indicated. OD will be equal to 1 meter as well. Okay. So if we use Pythagoras, let's call G plus F. Okay. G plus F. Okay, these are F. And let's call this distance D A D. Let's call it G, the distance between it. All right. So that G plus F is going to be equal to this, right? OD squared plus y plus root 2 plus h. Okay, so have that. We can as well, knowing that, let's let okay, let L be equal to G plus F. G plus F, or F plus G is equal to L, so that we can get L to be equal uh, to do that, I don't have it to be 1 squared plus 3 squared. Okay, right. This, which is going to give us 3.2 meters. So we'll have that. Then we can, using the cosine rule, we can just obtain F to be equal to, okay, the root of OA, okay, root of O plus 3 squared minus 2 into OA, okay, times 3 cos 90, okay, minus theta that we got there earlier on. All right, so we'll have that. So when you, which is plugging in all the values, okay, we arrive at it to be this 10 minus 6 sin theta minus 6 sin theta. Okay, then got L minus F from what we have, information we've given so far, is equal to G and is equal to H. Okay, so if we follow that, therefore H is going to be equal to 3.2 that we got in already, okay, minus this 10 point, sorry, 10 minus 6 sin theta, Okay. Now, having gotten that, we can now get y2 substitute 2 is equal to 3 minus h. Okay. And which is equal to, so to do that, we're going to have it to be equal to 3 minus 3.2, 3.2 minus this. Okay. 10 minus 6 sine theta. Of course, we know why we have this one to be sine theta, because 90 minus theta is, okay, is equal to sine theta. That's why we have sine theta. All right. So that if you consider the mass, the potential, the gravitational potential energy, call it this of G2 is going to be equal to m, the mass times the acceleration due to gravity, times y substitute 2. Okay. So if you plug in, knowing that v, the potential function, will be uh, w uh, y1, which is v substitute g1, okay, plus mg substitute y substitute mg times y substitute 2. All right. So if we plug in all our values there, we are going to arrive at 58. Of course, we know that the mass of the rod is 12 kg. We multiply it by 9.81. Do our multiplication there. We arrive at, do all the multiplication that we need to plug in all the values. Okay. We arrive at this sine theta. Okay. Plus 29 29.43 43, okay, minus 31, okay, 0.39, all right, minus 9.81, all right, into this 10, minus 6, because this is square root sine theta, sine theta, all right. So if we differentiate, if we differentiate this potential function with respect to theta, for course we want for our equilibrium position, okay, we are going to have it to be equal to minus, sorry, 58.86, okay, cos theta minus 9.81 one m into half, or minus half, okay, into 10 minus 6 sine theta, okay, minus half raised to power base minus 1.5 into minus 6 cos theta minus 6 cos theta. Okay, all right. So that's a bracket, okay. Okay. So we can now, if we equate this one to 0, if we put theta to be at the value that is given as 30 degree, we are going to arrive at the mass and solve it. We are going to arrive at the mass to be 5, okay, 0.3 kilogram. So this is the mass, the magnitude of the mass.